Cool. So today we're going to take notes on covalent bonding. And so last week we focused on ionic bonding, and then we learned how to name ionic or covalent compounds, but we mainly focus on ionic bonding. And with ionic bonding, elements either gain or lose electrons, and in gaining or losing electrons, they become charged, and then they hang out near each other because opposite charges attract. And what a chemical bond is one element is positive, one element is negative. They hang out near each other because of those opposite charges. Also, and I didn't really emphasize this, so I do want to just add this one thing. It's a little close, my hand gets in the way. For ionic bonding, it's always between a metal and a nonmetal. And it's easy to recognize because the metal comes first in the chemical formula. So we always wrote cation first, and the cation was the metal. And so in ionic bonding, it's between a metal and a nonmetal. The metal comes first. Covalent bonding is between two nonmetals. It's a bond between two nonmetals. And so if we're looking at the chemical formula, then nonmetals come first in that chemical formula because it only has nonmetals. And the biggest thing that you really need to take away about covalent bonding is it's not like ionic where they attract each other because of opposite charges. Instead, two elements share one or more pairs of electrons. I need to write neater, sorry. Two elements share one or more pairs of electrons. So I need a volunteer who can be an actor. I'll read you all your lines. Okay, come on down. Yep. Will you bring your pen? Okay. We're going to stand here so the people at home can see us too. You can be right there. Okay. This is Jackson Barnes, our actor. I'm this element, and I just have this one extra valence electron. And I really just need one more valence electron in order to become stable. So, you know, Jackson, I was thinking, if you could just give me that, that would make me happy.
No, because I want yours.
What are we going to do? How are we going to solve this problem? Ooh, I learned in kindergarten, maybe even preschool, that sharing is caring. What about this? I will share my electron with you if you'll share your electron with me.
Sounds like a plan.
All right, so we hold our electrons out. We each hold on to each other's, but look, oh wait, my pen cap kind of ruins that one. Hold it again. We're stuck together. Oh, now your pen cap ruined it. But the idea is now we are bonded. We're sharing a pair of electrons. So in ionic bonding, it's the opposite charges that attract. In covalent bonding, we're literally holding on to the same two electrons or the same two pens, so we can't go anywhere. Thank you very much. Can you give me a round of applause? Jason? I didn't give, I shared. So I still have access to mine and he still has access to mine. So it's sharing, it's not giving. We're both holding on to it. So now we're going to write the steps for covalent bonding, and then we're going to be doing some practice problems, and hopefully the practice problems will help the steps make sense. But just like last time, we're going to get the steps written down first, and then we'll practice it a bunch. Just so you know, that's where we're going to end today. We're going to practice some examples, and we're going to call it good. Tomorrow, you're going to have practice worksheets where you're going to be practicing these skills. And we're going to save our homework quiz till Thursday because this is a little bit of a harder concept. So I want us to give us plenty of time to practice it first. Okay. So the steps for covalent bonding. There's 5 steps. Bless you. The first step, oh, by the way, to do covalent bonding, I have to tell you the chemical formula. You know how in ionic bonding you figured out the chemical formula because you figured out how many positives and negatives you need to cancel each other out? Covalent is different. I have to give you the chemical formula first for you to follow these steps. So I would give you the chemical formula, and step 1 is to write Lewis dot diagrams for all the elements in the chemical formula. So the first step is write Lewis dot diagrams. Easy peasy. We know how to do that by this point. Step 2. Write how many times each element needs to bond. Again, these steps will make more sense when we actually do it, but we're just going to get them down and then reference them. Step 3 is connect the dots to the element that needs to bond the most number of times. And I realize you all think that's a hashtag, but to me, that's a number sign. I can't give it up. Used to be a pound button on the phone, too. You know that? Cool. Oh, cool. We're not hashtag people. I'm not either.
That was like a year ago.
Oh, that was so last year. Sorry. Redraw the connections. As dashes. 1 dash equals 1 pair of electrons. And then step 5 is to draw the unbonded electrons. All right, ready for some examples? All right. First example is methane. Have you heard of methane before? It's that ingredient in cow farts, causes global warming besides carbon dioxide. Its chemical formula is CH4. If you took away the H, it would be C4, but you need to put a 4 after the C. So this is methane. Methane is CH4. No, but it's not methane. All right. So step 1. Hey guys, stop talking, please. Step 1, write the Lewis dot diagrams for each of these elements. So how many carbons are in this chemical formula? 1. How many hydrogens? 4. So I write hydrogen 4 times. And so I have to draw Lewis dot diagrams for all those elements. So how many dots do I draw for carbon? 4. And remember, we go in order. We go top, right, bottom, left. So carbon has 4 what I call lonely electrons. They're not paired, they're alone. One on top, one on each side, one on the bottom. And each hydrogen gets 1 valence electron because hydrogen only has 1 electron total. All right. Step 2, that was step 1. Step 2 is to determine how many times each element needs to bond to be happy. We are still fulfilling the octet rule, which means elements want to have a full valence shell to be stable. Usually that means 8. And an easy way to figure out how many times each element wants to bond is how many lonely electrons it has. Remember when I bonded with Jackson? We did 1 bond and we each got 1 electron out of it. Carbon has 4, it wants 4 more, so it wants to bond 4 times. Now you also might remember when we learned about the octet rule that we learned that there is an exception to the octet rule, and helium was it, right? Helium is in group 18, but it only has 2 valence electrons. But we said it was happy and stable with that because it only 2 fits in the first energy level. Hydrogen is also in the first row of the periodic table. So hydrogen wants to be like helium. It wants to bond 1 time and have 2 valence electrons, and that makes it stable because that fills its first energy level. Can you buy that? Does it sound accurate? All right, we'll say it is. So each hydrogen only wants to bond 1 time. Now, in ionic bonding, when we were gaining and losing electrons, we showed that they were giving away electrons by drawing arrows to empty spaces. Do you remember how we did that? We drew arrows to those gaps. Step 3 says connect the dots to the element that needs to bond the most number of times. So we are not drawing arrows. We are not dealing with empty spaces. We are connecting dots. And the element that wants to bond the most is the element that everybody connects to. So everyone's going to connect to carbon. So I can connect this hydrogen to one of carbon's dots. And I can connect this hydrogen to one of carbon's dots. And the next hydrogen, it doesn't matter which dot, as long as you're always connecting a hydrogen to a carbon dot. So each of those connections is a shared pair of electrons. Okay. So carbon sharing this electron and hydrogen sharing that one. So those connections show the 2 electrons that are going to be shared between each other. And this carbon is sharing this electron and this hydrogen sharing that one, and so on. Our next step is to redraw the connections as shorter dashes, because each dash is going to equal those pair of electrons. Now, when there's one element that bonded the most, it goes in the middle and everything connects to it. So we draw carbon with a dash to one hydrogen, and another, and another, and another. So those dashes represent covalent bonds, and each dash equals a pair of electrons. There won't ever be more than 4 single bonds because you need to get up to 8, and each bond represents a pair. So if we're checking here, carbon has 8 electrons. It's stable because it has 2 here, because they're being shared, 2 here, 2 here, and 2 here. And each hydrogen's happy with 2 because then it's like helium, which is a stable element. Let's do another one. Let's do an example that you've seen before. Let's try water. H2O. So step 1 says to write the Lewis dot diagrams for all these elements. Oh, we skipped step 5 because step 5 isn't relevant in that example. We will do step 5 in the next problem and you'll see why. Thank you. I meant to mention it and I forgot. So we've got H, H, and O. So we start by drawing the Lewis dot diagrams. How many times does each hydrogen want to bond? Once. They only have 1 lonely electron each. How many times does oxygen want to bond? Well, it has 6, and it needs 2 more, and it has 2 lonely electrons, so it wants to bond twice. Everybody with me so far? Any questions? So when we connect the dots to the element that wants to bond the most. In this case, that's oxygen. So we can connect this hydrogen to one of oxygen's lonely electrons and this hydrogen to one of oxygen's lonely electrons. The steps will make more sense as we do more practice. So we redraw it as dashes. So this hydrogen connected once to oxygen, and that hydrogen connected once to oxygen. And now for step 5. Step 5 is to draw the unbonded electrons. Who has electrons here that we didn't connect? Oxygen. It has 2 pairs of unbonded electrons. So we draw 2 pairs of unbonded electrons. Does that make more sense now? Sometime you'll have unbonded electrons, sometimes you won't. Depends on the elements that are bonding. Let's do another compound that you've heard of before. Let's do carbon dioxide, CO2. And I'm going to kind of pause so that you can get ahead of me and try to follow the steps on your own first. So we've got carbon with 4 dots. Each oxygen has 6. Carbon wants to bond 4 times. Each oxygen wants to bond twice. So what are we going to connect everything to? Carbon, the one that wants to bond the most, right? So we connect everything to carbon. And each oxygen gets its lonely electrons connected, and carbon gets all of its lonely electrons connected. And when we redraw this, the one that bonded the most goes in the middle, but I'm doing something different here. This carbon connected to this oxygen twice, so I do 2 dashes. And this carbon connected to this oxygen twice, so I do another 2 dashes. Those have a special name. Those are 2, it happens to be 2, double bonds. When you did 2 connections, we do a double dash, kind of looks like an equal sign. And that one happened to have 2 double bonds. What am I missing in my picture? No, because how many times did each oxygen want to bond? So the one that wants to bond the most always goes in the middle. Unbonded, and they go on oxygen, right? Each oxygen has how many unbonded electrons? 4. So just draw them as 2 pairs around the oxygen. And that's what carbon dioxide looks like. And you might be sitting here thinking, why is she drawing them like on the corners instead of like the top or the bottom or the sides? Because I'm drawing them the right way, and it's really complicated, but to summarize, like electrons take up space and they want to spread out as much as they can. So going on the corners is better than top, bottom, or sides, but it doesn't, and bonds take up space. You don't need to know that. Also, if you had drawn water straight instead of bent, I would not have marked off because we are in 9th grade chemistry, but I'm drawing it the correct way because I have to. I'm a rule follower. So these are 2 single bonds, 1 shared pair here, 1 shared pair here. These happen to be 2 double bonds. They're sharing 2 pairs. They're sharing 2 pairs here as well. This one up here is 4, what type of bonds? 4 single bonds. So now let's do one that has another type of bond. Let's do N2. That's nitrogen gas. It makes up 70% of our atmosphere. When you breathe in more nitrogen than anything else. So we draw our ends. How many dots do we need? 5, that's right. How many times does each nitrogen want to bond? 3. They each have 3 lonely electrons. So we connect those dots, lonely electron to lonely electron. Since there were 3 connections, we draw a triple bond. And FYI, there is no such thing as a quadruple bond. So you can either have single, double, or triple. That's it. So you just learned all 3 kinds. So I want to wrap this up a little bit early today. We're going to do one more example. I'm going to write it down. I want you to try it. And then we'll keep practicing this tomorrow. I want you to try NHI2. That's the number above in red. You just look at the second. You see the nitrogen here, the copper is falling, so it's 15. See that? The one that wants to bond the most is what everything connects to. The one that wants to bond the most, the 3 that you right. Oh, okay. Oh. Yeah. So are you allowed to use the hydrogen? Ooh, close, not quite. We're gonna go over it. Okay. So we start with our valence electrons. Nitrogen has 5. Hey guys, please stop talking. Iodine has 7. How many times does nitrogen want to bond to become stable? 3. How about hydrogen? Once. Iodine? Once. And once. Now, When we connect the dots to the element that wants to bond the most. That's why we took the time to write how many times each one wants to bond. Because nitrogen wants to bond 3 times, so we bond everything to nitrogen. So hydrogen connects once to nitrogen, iodine connects once to nitrogen, other iodine connects once to nitrogen. We always do the lonely electrons, so everybody's happy, right? Nitrogen got all 3 bonds it wants, and each of these elements wanted 1. So when we redraw it, the one that bonded the most goes in the middle. It bonded 1 time to hydrogen, 1 time to that iodine, 1 time to that iodine. And now we go back and do the unbonded electrons. And if we did this neatly, it's pretty easy. How many does nitrogen have? 2. How many does this iodine have? 6. And then this iodine also has 6. I realize my eyes really look like sideways H's. So our picture should look something like that. What type of bonds are they? Single, double, or triple? Single bonds, but there's 3 of them. So a single bond means we connected them once. When we connected those dots, we did 1 connection between iodine and nitrogen, 1 connection between hydrogen and nitrogen, 1 connection between the other iodine and nitrogen. When we did a triple bond, it was 3 connections between the same 2 elements. But here there's 3 connections, but they're all to different elements. So those are 3 single bonds. So tomorrow we are going to do a practice worksheet where we're just going to practice, and get comfortable with these steps. Thursday, we're going to have a homework quiz on it. Wednesday, you have a lab to do that actually will take some time and require some materials. Okay, so make sure that you are doing the lab either in advance or you have time on Wednesday to spend about 45 minutes to an hour doing the lab. All right, I'm going to stop the recording because we are done. If there's any questions at all, I'm available.